up until very high temperatures, which uranium nuclear rods, once they're melted, are very hot. And they ended up burning through the system, corroding through it, and ended up causing one of the worst nuclear spills that we have seen, one of the worst nuclear incidents we have ever seen. And this was something, looking in retrospect, we think we could have predicted. Like, Japan is known for tsunamis. We know that they're building these on the coast, so they're more susceptible to the elements. But nobody would have thought that the nuclear rods would have melted through all of its containment into the zirconium and causing the corrosion at that level. Next slide. And so when we look at this, we think, can this have been prevented? And in retrospect, yeah. I mean, looking back at it, we think, oh, of course, that should have been known. That should have been obvious. But at the time, it wasn't. And now we can think, is AI the solution for this? And not just for this problem, but for corrosion across the board. The National Association of Corrosion Engineers, NACE, and I'm going to refer to them different times, so I'll just use NACE. But they've estimated that the global cost of corrosion is, in 2002, $276 billion, which for today would be $490 billion. And then their estimate in 2017 was $2.5 trillion, which is $3.3 trillion that goes into either fixing corrosion, adapting to it, changes, whatnot. And if there's a way that we can use AI to maybe minimize this and maybe minimize disasters that occur, that could be something that we could look into. Next slide. So how can AI help? One of the best models for this is data and model training. So this is basically taking different corrosion behaviors, different environmental factors, temperature, pressure, reading it into a system, and then having historical data based off of this. So maybe taking our Fukushima Daiichi incident, putting that into our system, and then being able to have AI model and design potential flaws with the system. Having AI tell us that, hey, this could be a problem in the future. And its job would be to come up with situations like the Fukushima Daiichi, is that this very, very specific circumstance could possibly occur. So what can we do to prevent it? The other is predictive modeling, so giving forecasts based on this, being able to then read in data and change its forecast and predictions based off of that. So if you're reading a system, being able to take in the pressure and then notice if there's a pressure change, a temperature change, and then adapting and changing and being able to tell us what we need to do. That, hey, the pressure went up, I'm going to adopt this, I'm going to change this factor. The one I thought was most interesting was the integrity operation windows, which is pre-testing set parameters in order to assure equipment integrity. A lot of times we see this kind of as the safety factor as to how much can a material or a component handle its stress or the load or whatever we're putting onto it before it fails. And a lot of times we put in, for depending on different things, we'd have different safety factors. So if it's a plane, you'd probably have a higher one for things that are easily replaced a little bit later. So this is something that would help us determine what would be a good safety factor given the different situations, the environment, and the likelihood of corrosion showing up in that situation. And the easiest would be the visualization and presenting. So we can see here, these are actually SEM images of corrosion materials. These are various levels of corrosion, which with AI, we could hope that we could take this and learn about it on a much more deeper level, actually understanding this, maybe even looking at it in a 3D model as to how the corrosion affected the material across the shape. Next slide, please. So AI and corrosion inhibitors. This is probably the aspect that most engineers would look at and be like, hey, we should do this, is can we coat the material? Can we coat the material? Can we look at a material and maybe add something to it? Maybe possibly look at the situation and how can we prevent corrosion from even being a problem? And the current issue with this is that it relies on a lot of trial and error, a lot of experimental testing. And it's not necessarily the most applicable on a large scale. What's also interesting is that corrosion inhibitors were also mentioned in the Quran. So this is Surah Al-Qaf, verse 96, 97, and this talks about the situation in which Gog and Magog, so Yajuj and Majuj, were entering into the north, and Cyrus had told the people there to bring him a block of iron, but also bring him copper. interesting about this is that he was mitigating corrosion. He was trying to create a system in which iron, which is highly susceptible to corrosion, and adding in molten copper to help prevent corrosion or degradation of this material so that it could put up a large-scale defense against Gog and Magog. And it worked. They actually were not able to infiltrate it, and the building that he had created ended up sustaining against that invasion, protecting the north. So we can see that this is something that we see even in the Quran about how we can blend different elements that Allah Ta'ala has given us, different materials, different factors, and create something that might be better. Next slide, please. And this brings me into actually what my research was in, which is molten salt corrosion of coated and uncoated stainless steels in sodium chloride and a potassium chloride mixture. So this is basically a thermal energy system. We were testing if a material worked better in a molten salt environment, because for nuclear power plants, one of the biggest issues is how do you come up with energy when it's non-daylight hours? What can we do so that we're not reliant entirely on the sun, or if it's a cloudy day, or if we're building somewhere that doesn't really have a lot of sun? And one of the solutions is to come up with salt as a heat storage. And basically it would melt and then solidify, and that would help with the heat storage. However, salt is highly corrosive. It's a very, very corrosive element. That's actually what causes a lot of the corrosion on beachside houses and whatnot, is the salt water. So our experiment was looking at different salts and looking at different steels in this environment, but also testing if we dip them in a aluminized coating, would that help mitigate the corrosion? And we can see here that it actually did not. So it actually did not actually end up helping that much. This is an example of a carbon steel, but the stainless steel 316, which is one of the most commonly used stainless steels, ended up being the best, and the uncoated version as well. But even on these, we can see that on the next slide, sorry. That the maps, so these are SEM maps. These are showing elements in terms of how they are. So we would have iron, chromium, oxygen, and nickel. And in the aluminized coating, which is what we coated the material with, we see the aluminum in the pictures on the right side. On the left side, I'm sorry. But we can see how having the aluminized coating didn't actually impact our surface that much. And we can even see in the uncoated version that some of the corrosion is actually more uniform across there. And we see a little bit more uneven corrosion when we looked at the aluminized coating. And so it's kind of interesting to see why that might be, given that the assumption was that aluminum should have helped mitigate the corrosion. And this is actually one of the issues that we were talking about that AI could possibly help us fix. Because these were individually taken, sized, cut, prepped, and then covered in aluminum using a galvanic system to be able to aluminize these, which is a long and tedious process. And if you mess up at any point, it ends up messing with your entire study, right? So if this is something that we can help mitigate with AI, then that could be something that we could look into, maybe not having these gaps that human error could possibly cause. Next slide. However, AI is not perfect, and we all know this. I actually put an example of me asking ChatGPT to write the bio for our presentation here. And you can see that the information I gave it was it was not that much. It was very it was my name, my undergraduate career, what I focused on. And we can see that AI actually elaborated a lot on what it thought it should. So we can see that this is an issue, right? There's also various other issues, right? But in our specific system of using AI for corrosion prevention and management, one of these is the overcorrection, right? That's a possible issue, is that if we have AI deciding when to change temperature, when to change pressure, when to change other factors, other variables that we've put into place for a system that we're assuming to work a certain way, then could it overcorrect? Could it maybe possibly read the pressure at one point as being higher when it's not, and then maybe correcting our temperature and now putting us into a bigger problem? There's also issues with non-sanitary and large-scale applications. So how do we apply a computer system to something that's possibly moving. Like if we're trying to prevent or even manage corrosion maybe on an airplane, how does that work? Right? Are we looking at it for pre-flight, post-flight? Are we going to create some sort of system in which AI can also be mobile? Right? This is something to think about. And the biggest issue, in my opinion, because we ran into this, is large-scale applications. Is that it's easy to do something on a small scale, but then moving on to a large scale and trying to apply that on a large scale, right? So even for our research, aluminizing small particles of material, small pieces of metal was easy, but how do we do that on a large scale? How do we take a very large piece of metal and aluminize it in a galvanic system, which has to be submerged? And can we do that? Right? So even for AI, like we have to look like how accurate would AI be if our system is very, very large. If we're looking at maybe a nuclear system, if we're looking at a CSP system that are very large systems, how accurate can AI be? And if it is, like, is it maybe changing? Is it maybe, like, how is it looking at that, right? And then questions of accuracy and the limit of its knowledge. So AI is, again, limited by its knowledge that's fed into it. So I'm going to bring us back to the initial question, is that could AI have prevented the Fukushima Daiichi incident, right? It's like we think that AI could have, right? AI should have known that maybe there was a chance of a tsunami coming, given that tsunamis do hit Japan, right? There's a chance that it would knock out the power and prevent the engineers from being able to access the plant, right? We should have maybe considered that it would overheat and what would it do once it did, right? These are, again, things that we think we could have prevented, we could have thought about, or that now have happened, and we can, but can it actually know something that it doesn't know can happen, right? Like, is it capable at that point to actually have prevented maybe something like Fukushima Daiichi, which in theory we like to believe it could, but again, next slide. That's actually the end of my presentation. If anybody has any questions.
Thank you so much. That was such an interesting talk. And with that, I'll hand it off to Junaid Malik Saab to introduce our second speaker.
Ji, Assalamu alaikum. So we'll hold off the questions until the very end. A little bit of introduction about myself. My name is Junaid Malik. I am a civil engineer by profession. I work for local government in program management, project planning, and capital budget planning. And with us today, we have Atahul Wahab Ahmad Saab. He's going to be talking about his topic, AI for HVAC building systems. Atahul Wahab Ahmad Saab has a background in mechanical engineering, project management, and defense financial management. In the mechanical engineering domain, he has worked on negative pressure rooms and ventilation systems in nuclear environment, building front-end management systems, commissioning of engineered systems, systems engineering design, and HVAC controls integration on commercial buildings. He has worked on diverse projects supporting multiple federal agencies. Atal Wahab Ahmad Saib also teaches Wakfino students during their annual expo. So with that, I want to pass it over to Atal.
Jazakallah for the kind introduction. Assalamu alaikum. I'm asked to talk about HVAC systems and the emerging of AI. So you can please put the slides up. Okay. All right, next slide, please. Okay, so all right. So here is a cutaway view of an HVAC system. As you can see, it is mechanically designed to provide comfort and save dollars as well. So this particular design, as you can see, has an outdoor air intake and a return air intake, and it has the damper fresh air intake. It has a preheat coil, and the purpose of that is to bring in fresh air if it is cold outside and um, heat it to a certain temperature. So when the actual zone calls for a conditioned environment, the unit does not have to work hard and it can efficiently provide the desired output. So then you have a bag filter configuration, and then you have a cooling coil. The cooling coil can be either like a chilled water cooling coil running by chillers, or it can be staged DX cooling. Let's suppose if it's run by, can you hear me? Let's suppose if it is run by chillers, if the chillers are feeding the cooling coil, typically in commercial setup, there are, let's say, normally 2 chillers or more. So where AI can help with this one is it can set the run times equally. It is not like the primary chiller keeps on running and the secondary chiller only runs when the zone demand calls for it. So that is the benefit of AI. It can interchange the chillers if you have a chilled water system. And then you have a reheat coil. It can be a steam heat or hot water heat. And then you have a fan. Typically, it has like a VFD, variable frequency drive, for energy savings. And with AI system, with AI building management system, it can detect early on when to turn on the fan, at what speed to turn it down. So that is where some of your energy savings come in as well. Okay, next slide, please. So the way the HVAC industry here works is with all of these various aspects, and I have converted this into 5 layers to help you understand it better. So the first stage is, for example, your mechanical equipments, air handling units, chillers, boilers, cooling towers. And then the second layer is the sensors, or your VFDs for your fans or actuators for your dampers, flow sensors, CO2 sensors. And the third stage, you can say, is the controllers, the PLC controllers, which in technical term they call slave controllers. They control each unit individually. And basically the sensors give them the input and the controllers provide commands or output to each respective unit. And then on top of that sits the building management system, where a building technician can monitor either on his laptop or a computer all the functions of what's happening inside the building, like, for example, which VAV boxes or, dampers are on or off, which air handling unit fans are running, and what is the condition of each zone. So, and then on top of that sits an AI cloud optimizer. So the way it has 4 capabilities: predictive AI, load forecasting, energy optimization, and digital twin simulation. These are the 4 aspects of the AI that help condition your BMS system better, and it feeds command via the global controller. And so basically the beauty of it is not one aspect of it working individually, but all of them collectively providing the desired output. Yeah, next screen, please. I think you missed one. Can you go one by? Okay, all right, let's go to the next one. Okay, now since AI is, with the building management system, the functionality of it. So here is a little comparison of the outputs of a traditional BMS versus an AI-powered BMS. Traditional BMSs are reactive. They worked on fixed sensors. AI-powered BMS works on multi-source data fusion, which means it gets its operations better each time by collecting data not only from the individual building, but also from the respective buildings in its area, like what are the weather conditions and so forth, like that as well, and what makes certain building more efficient. So it gets all that data, and that's what they mean by multi-source data fusion. And then on the intelligence layer aspect, it has fixed rules, if-then logic, PID controllers, and schedules based. We know if something is not operating, if someone is working later than 5 p.m., like say the schedule is on occupied mode, and someone's staying late working, they have to manually control that schedule through the BMS system. While the intelligence layer for the AI system is predictive AI. Uh, Sorry, it comes with a digital twin first. First is a digital twin, which provides a calibrated model, and then is the load forecasting. It uses that model to predict tomorrow's demand, and then it does predictive analytics, which schedules the preconditioning of the equipment and maintenance actions. And then lastly is energy optimization or model predictive control, which executes those plans in real time while continuously adjusting equipment to actual conditions. So when these four aspects of AI come together, they really provide good energy savings. Okay, and then we have all right. So here is a traditional AI-powered BMS. You can see the traditional BMS is reactive while AI is proactive. Traditional BMS responds to set point deviations, while AI has the capability to do load forecasting that gives the system an economic and operational intelligence layer, and AI allows continuous model calibration. And yeah, next screen. So here is a comparison of a 200, of a typical office building. Um, let's see, 20,000 square feet office building, and the way that the energy is saved. So the dotted line is your typical BMS, and your solid line is the AI-powered BMS system. And then you can see your energy saved is the differential between the two curves, and that translates into kilowatts saved, and eventually your dollars saved. And here is how an AI typically works. It collects data from your physical buildings via the HVAC sensors. It runs simulations via digital twin virtual model, and then it comes out with the best planned scenario, and then it continuously optimized control commands are sent to the HVAC system, and then it does that continuous calibration, model calibration. That's it.
Jazakallah ta'al Wahab Ahmed Sahib. This was a great presentation, also very technical. So I would like, now we have a few minutes for question and answer. I would like to open it up, Hadia Sahib, if you're good with that, with Touba Shah Saiba. If there are any questions, for her, from the lady side first.
Assalamualaikum. We don't have any questions at the moment. We can start with you guys.
Okay. I think if you can speak a little bit louder, it's very hard to hear. Okay, so I'll be the first one to ask, and then I'll pass it over to others here. Jazakallah for an excellent presentation. Yes, we all take corrosion for granted, and it's kind of like, out of sight, out of mind. If we just think that this is something that we paint over it, or we just take care of it visually. There's so much going on. I personally have to deal with a lot of underground infrastructure that comes in contact with soil. And I am very concerned about the health of our infrastructure, and part of it is due to corrosion. So, in your studies, my question is, how do you? Yes, you are testing stainless steel and other materials, but how do you kind of modify your approach and you apply it to, for example, I deal with infrastructure, right? I mean, underground infrastructure, a lot of pipes, a lot of metal pipes, and how do you apply that AI approach to some of that? Jazakallah.
Yes, that's a really interesting question, and that is a really major aspect. I mean, I spent my college time in LA, that's one of their biggest problems, the underground corrosion. And so I'm assuming that they would, for underground system, I'm assuming they'd probably have some sort of system that's similar to like cathodic protection, which rather than them pulling out like the pipes or doing that sort of thing, they're able to do it from a surface level. They're able to like detect this from a surface level. They're able to like connect probes and whatnot, maybe underground at some points, and various different points across the pipe, and then have it connected to an overground rectifier that then ends up going underground as well. So rather than them having to pull up all of the streets of LA and redo all of the piping, right? This is something that they use a lot there, which is cathodic protection, right? So they end up placing an anode into the ground, have it connect to a rectifier, and then have it go down and connect to our piping, which is essentially our cathode, right? So I'm assuming that if AI had some sort of modeling that was similar, it would probably work in some way that is similar to that. But this does again bring up one of the issues that with the AI is that how does it apply to these sort of things? Even researching for this right now, like there isn't really a lot of concrete evidence on how we can use it. And I think one of the biggest issues with why corrosion is as much of an issue as it is that it's unpredictable. We can have as many models as we want. We can have all sorts of like things, but there are factors that we might not account for. And that's hopefully where AI would fill in those gaps, right? The hope is that AI would look at those and maybe even on just, maybe if not on a management level, at least on a prevention level, I think AI might be able to help us in those regards. So maybe before dealing with, like if we're building a new building or whatnot, maybe having like soils, like samples of it, being able to test for what material is already there, what's the composition of it, and then have AI tell us that like, hey, you know, like maybe stainless steel 316 isn't your guys' best option. You know, maybe look into a different steel, like maybe look into this other aspect that could be better, right? Maybe having us being able to tell us based off of the individual soil samples that we give it, right? Those are the factors that we would put in to be able to then help us with prevention. Management, I think, is a little bit harder, but I think with corrosion management in general, I think that is the issue, right? Is that what do we do to already existing infrastructure, right? How do we make it more sustainable? How do we prevent issues with it as well, right? Like if we already have planes in circulation, how do we prevent the corrosion that's going to happen there? And I think that might be something that AI in the future could help us with, right? Maybe be able to look at the systems and tell us like, hey, like this could be a possible thing. Or if you already have corrosion on a system or already have something, right? Either something similar to the cathodic protection or maybe some aspects of it that are looking at it and being like, what can I do, right? Because obviously replacing infrastructure is expensive, right? There's an environmental aspect, there's a lot of like money aspects, there's a lot of like just random infrastructure, right? We can't just be tearing down buildings because they're starting to become wobbly, right? And we could in some situations, right? But maybe not in all of them, right? And even if we do, how long is the downtime? What is that kind of situation, right? So that might be something that AI looks into in the future is what can we do for already existing infrastructure that might be in high corrosion environments, right? And then the new ones that we are building, maybe giving us better predictions for that, maybe giving us better information for how we can prevent it, or if we do update the system, right? Like with safety factors, we know that we're pulling out material that is still capable of working, but just in case we're pulling it, right? So something that maybe is partially used in that sort of way, maybe AI could give us some ideas of what could be a possible band-aid to maybe get that piece that's already working, just working a little bit longer. So I do think it's something to consider as terms of like what AI potentially has the ability to do.
Jazakallah. Assalamu alaikum. This is Mustafa, serving at Humanity First. So my question is actually for the both speakers. The first question is, so one disaster actually happened. So the presentation actually mentioned about tsunami and few other disasters as well. So my question is, how can like our disaster relief organization would be able to use AI in terms of either it's post or pre-disaster situation, whether like where to give more help during the disaster time. What would be the best solution like to implement? That's my first question. And the second question is like, so when I was doing a project in Ghana, and I start seeing like few Ghana schools, and I see that like they have like really like poor HVAC system. They don't really have it. Like I see the students are actually struggling. How can we have like a HVAC system using AI or anything, which is supporting like a sustainable green community that can also give comfort to the students, and that would actually help to concentrate and like give comfort in their lifestyle as well. So those are my two questions. Jazakallah.
Assalamualaikum. This is actually a really interesting topic because while I was researching for this, my husband and I had actually gone into a long discussion about AI and the uses in disasters, which I think in those situations, what might be a good aspect is combining different fields. So I have experience working with like GIS systems and like LiDAR and all those kind of systems where you're graphing and mapping and looking at those kind of surveillance situations. And I think something for a disaster situation would be maybe using AI to fly maybe some sort of drone or some sort of mechanism that is able to survey the system for us ahead of time. So be able to survey, for example, like the Fukushima Daiichi incident, right? Have it go in and survey what the situation is, right? Because the main issue with the Fukushima was they couldn't get into it because of the water, right? Like they couldn't enter the system because of water. So if we can have maybe like a drone or some sort of other satellite system that is able to look at like already established satellite systems, maybe look into what these things are, and then having AI then give us predictive modeling, right? Tell us that like, hey, like your reactor bursted here, right? There's a potential of it spreading in this direction, spreading in that direction, right? So rather than us trying to do control afterwards, at least helping us with the prevention, right? Being able to tell us that if most of our nuclear waste is coming out towards the south, right, where does it have the potential given the currents at that time, given the wind speed at that time? Like, which direction is it most likely going to travel? And then already having somebody there to maybe stop it, right? Or if it's in a situation that's already happened, right? Having somebody go in and be able to have AI tell us that, hey, like, this was a building here before, right? So you will have this level of contamination at this place, right? You would have this level of contamination at this other place, and these are possible materials that you can use to rebuild, right? So maybe just to make the process post-disaster a little bit more efficient, because the idea hopefully is that we wouldn't have to use people to do the surveying, right? We wouldn't have to use people to go in and do the experimentation. We could have AI give us some base level to start with, right? Like have them go in and have AI go in and come up with some sort of plan that then the engineers, the architects, you know, they could go in and solidify or implement. But at least having AI do the groundwork of disasters, or maybe helping prevent too much of a disaster, right? Depending on how quickly we're able to recognize what the situation is. And then again, implementing some of these other things that we're talking about, right? Like if we do have like an earthquake, right? Like being able to tell us where the most damage might be and where would be like, or surveying the area and being like, hey, like maybe start here, right? This would be like the most efficient place to start. Or this would be like, maybe don't put as much effort here right now, like maybe just clean this up. Or maybe this is a low contamination area, so like we can wait for a second, but this is a high contamination, so we need immediate attention at this point. So just something like that, using, I think AI as a...
Are you talking about air conditioning in what area of Ghana are you talking about? City or remote areas? Okay, what kind of systems do they have?
In general, I'm just talking about general people.
Yeah, you see, the presentation I gave was mostly about here in this country. But one beauty of BMS systems is once you have it installed over there, you have to get some technical expertise. But with the BMS system, you can control it from here in this country if one is willing. So you don't have to give them the training. But if you like it depends on Jamaat's priorities. Do they want to give them a building, or do they want to invest more on HVAC systems? It all depends. So yeah, it is something that can be thought about. Yeah.
Jazakallah. Okay, we still have some time, so
Oh, Assalamu alaikum. We have a comment in the Lajna.
G, go ahead.
Assalamu alaikum. I just had a comment for Touba. I have a master's in emergency architecture, and I think some of the conversations, even about HVAC, I think this is the point where like you were saying, you have to connect the fields, because even the HVAC issue, before we even get to I think it's, what are the local systems that are being used that are working in places where the resources are, they're scarce. So you're not going to bring an AI system to work the HVAC for a school in the middle of, in the middle of nowhere. So these are the kind of places that people are working in, right? So I think it's like thinking about the team that you're working with and what are the expertise there, because there may be local systems for HVAC and just airflow and things that work better for the materials that are being used there. So maybe that's something to think about, to not let go of kind of the vernacular architecture, because a lot of times that works better and you have less of a maintenance issue. And then the other thing about the GIS, just the comment for Touba, that in my master's program, someone was actually doing that kind of research where they were looking at models of changes that happened within geography after certain disasters. So I can share that with you. Yeah.
Jazakallah. So with that, on the second topic about AI for HVAC building systems, any questions from Lajna side for Atal Wahab Ahmed sir?
I had a question.
G, go ahead. Go ahead, please.
So you talked about that this new AI mechanism, but I wanted to know, and I think it sort of piggybacks the question about Ghana. So a lot of our carbon footprint comes from old existing buildings.
Can you please speak up? I'm sorry, cannot hear you.
Oh, sorry. I was saying that a lot of our carbon footprint comes from old existing buildings that have outdated mechanical systems. So do the building owners or the people have to buy new and expensive equipment that is compatible with AI, or is there a possibility that they can just install the AI software on the existing outdated mechanics, and what is that transition going to be like? And is it affordable? Is it sustainable in the long run?
Yes, it depends what kind of resources you are looking at. Like, for example, I remember the Baltimore Mosque. I was sent by Daud Saab over there. He was then the property secretary to look at the systems, and they had really very outdated systems. Now they have, alhamdulillah, new systems, but you see new systems have better EER rating, and it will provide more efficiency. In order to take better advantage of AI, you have to have good systems. The newer the systems, the better, because they are more efficient. And with AI on top of it, because the presentation I made was about the BMS systems, which is how they control the HVAC unit. So it all depends on what kind of investment you want to make. But as far as from the operational standpoint, they have determined this for a 20,000 square feet building and also 200,000 square feet. I was looking at both models. They give you energy saving from 20 to 40%. So yeah, in short, if you have newer systems, the better for AI. Jazakallah.
Jazakallah. Any other questions from Lajna side?
No, Jazakallah.
Okay. So I have a few questions for Ata Ahmed sir. So the topic that we're discussing here is AI, and one of the things that I want to understand, I think we use a lot of technical jargon. So before we get into AI, I think you mentioned about BMS, right? What does it stand for?
BMS is
Building management system. Okay.
It is the one where all the inputs are fed.
All the inputs. Okay. Okay. Yep. Okay, so do you want to explain that? And then I have a few more questions.
BMS means Building Management System. It's like a computer system which is interlinked with a global controller, and it gets all the input from all your sensors, from all your VFDs, and all the equipments out there, and the building technician cannot see all that in a screen. And then he has the capability for a traditional BMS system, he has the capability to override certain things. And just by the way, those building technicians are not happy because they think they'll be out of a job. So
Understood, understood. So, and you also mentioned HVAC, which is heating, ventilation, and air conditioning. And you also mentioned something about digital twin. Can you talk a little bit about what is a digital twin?
yes, this is something I researched about. I have not dealt with it directly myself. So the way I was researching was how the AI works. So basically, they say digital twin, it provides a calibrated model. Like it's not a real model, it provides a calibration, like, okay, this building has these many equipments. If they run during, for example, it will be, okay, if it runs during when energy is low, you know utility rates sometimes are higher. So it will precondition the building, pre-run the building. So it will try to see if it can save energy, for example, save you dollars. Depending on how much load, meaning how many people are in certain room and how much the air conditioning is going to be utilized, for example, or heating is going to be utilized. So it determines if it, during cheap utility rates, if it can run most of the equipment.
Jazakallah. This is more of a question, I guess, for both speakers. Um, we all understand that AI, artificial intelligence, is based on the data. And the better the data, the more robust the data, the better the outcome. So I am curious on a system like, we talked about, let's talk about cathodic protection first, or I'm sorry, not the corrosion part of it, and also HVAC. So can you guys talk a little bit about like where do you house this data, and like how do you run like a data, like what do you do to kind of clean the bad data from a good data, and use it for your decision making, or AI decision making? Did that? Yeah. So Touba, do you want to take a quick stab at it? I know we're just a quick input.
Assignment? Okay. I guess maybe looking, because yeah, that is a really good point, right? If we're feeding in data, we're feeding in, like decades of information, and some of that information might be outdated, right? And obviously, we don't really want to have maybe a person going through and filtering it, even though that might be the most effective way, right? The most accurate is having an actual person going through, but I think maybe coming to some middle ground would be that, like, going by certain time periods, right? Or if we're looking at certain aspects, say that we're looking at like LA, we're looking at like, if we're cathodic protection, for example, right? If we're looking at LA, we're looking at major cities, we're looking at DC, we're looking at Baltimore, right? Maybe having AI sift through a certain amount of that data, and then having an engineer that like verifies it, and then tells AI that like, hey, yeah, like you did a good job, like, you got like 85% of it was good, versus like telling AI that like, hey, no, you only got like 60%, right? And then essentially, right, AI should be able to learn, right? AI, that's what AI does, right? It learns, it takes the information, and it takes like, okay, this person gave me an 85, like that means certain things that I already checked, that's what I need to present more of, right? And then having it maybe sift through the next couple of decades, right? And then going through, and then hopefully the idea is that in the beginning, it would maybe take a little bit more time, right? Like maybe we could only do 5 decades at a time, right? Have AI do that before we need an engineer to go in and clarify it. But the idea is that as it's going, right, it should be adapting, it should be learning, it should be able to take in that information and change and get better as it goes. And that hopefully we would get to the point where maybe, like half a century in, right, we're not maybe going through as much, right? We're going through maybe like a few, like we're having it go through a larger period of time, right? Or maybe we're giving it more cities to go through because the model has gotten better. I think that might be one of the ways to do it, but I do think, again, at least in corrosion with AI, it's really in a very elementary state, right? We're looking at like very 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 beginning stages of how we can use AI for corrosion. And again, like it's a really complex topic, so I think AI might need a little bit of help in the beginning. Like in my opinion, I think it might need a little bit more hands-on from the engineers in the beginning, and then maybe after a while it should be okay.
Gee, I concur with that as well. Similarly, with HVAC systems, AI not only looks at data for your specific building and then runs simulation based on the data, and that data is typically for this BMS system will probably be run at the global controller level, and basically it also sees the data from other similar buildings with similar temperature zones like you, and then comes up with the best model, and it will also determine, okay, this building X, for example, has this many people, and this building that Ata is running wants to know. So it will help him, for example, and tell him that, hey, this is how they're running their equipment, and they almost have the similar number of employees like your building, and it will help you. So for example, one way it can help also is if for example in your building people leave on a Thursday for a happy hour, let's say, and the technician scheduled it for 8 to 5 during occupied hours, they will say, okay, it will automatically turn it off. That's the beauty of AI. And say if you are in another building that works late on a Thursday, instead of closing at 6 p.m., you close at 9 p.m. That you don't have to do anything with the HVAC equipment. It will automatically turn it on because it has got the data not only from your particular building, but it also has the data from other similar buildings. What to do and how best to run those equipments.
Jazakallah. At the end, I really want to thank both of these speakers. Thank you for your research and sharing the great knowledge with us. Inshallah, we'll be in touch. This is a topic that we all need to learn about. Inshallah, at another opportunity, inshallah, we'll do that. So Jazakallah. Hadi Sahaba, anything from you, from your end?
No, Jazakallah.
Jazakallah. So, Assalamu alaikum.
Junaid, do you want to do the closing session announcements? It's on the.
I don't. Okay, let me.
Oh, geez.
Do you want to? I just don't have it in front of me, please.
Oh, there's on the. Okay, I can. So, this is our closing session for the parallel session. After this, we have lunch from 12 to 1:30 p.m. In the men are, both of them are on this floor. And then from 1:30 to 2:30, we have Juma, which is in the basement. And this is where the men and women after lunch can put up their posters for the Abdul Salam session. And then the next joint session, IEEE, is going to start at 3 p.m. In Salon 1 and Salon 2.